Hello, everyone. My name is Wang Yufei. I am a PhD student from Northwestern Polytechnical University. Our work, Improving Depth Completion via Depth Feature Upsampling, has been accepted by CVPR24. Depth completion aims at estimate the dense depth maps from sparse distance measurements, which has attracted extensive research interest in industry and research communities. The encoder-decoder network, EDNET, is a commonly employed choice for existing depth completion methods. Recently, some works propose to employ the Spatial Propagation Network, SPN, to further improve the result of EDNETs. Although existing EDNETs-based methods have achieved considerable success, the EDNET is often employed as a black box. How the network recovers a dense depth map from the input sparse depth has always been ambiguous. In this paper, we visualize the internal feature maps to analyze how the network densifies the input sparse depth. We find that the encoder feature of EDNET focus on the areas with input depth points around to obtain a dense feature and thus estimate complete depth. The decoder feature tends to complement and enhance the encoder feature by skip connection to make the fused encoder-decoder feature dense, resulting in the decoder feature also exhibits sparse. However, EDNET obtains the sparse decoder feature from the dense fused feature at the previous stage, where the dense to sparse process destroys the completeness of features and loses information. To address the issue, we present a depth feature upsampling network, DFU, that explicitly utilizes these dense features to guide the upsampling of a low-resolution depth feature to a high-resolution one. The guidance feature can be obtained from any EDNET, including single-branch EDNET, multi-branch EDNET, and SPN-based methods. The multi-scale dense features that cover comprehensive scene depth information can progressively resolve ambiguity in super-resolving the feature of uneven depth distribution areas. Meanwhile, the upsampling process can also effectively integrate these dense features into the H or depth feature to predict the dense depth. To reduce computational complexity, we first reduce the channel number of these guidance features to the same as the low-resolution depth feature. To fully exploit the potential of the guidance feature, we propose a confidence-aware guidance module, CGM, which first filters out unreliable values of the depth feature by predicting its confidence map, and performs the guidance operation with adaptive receptive fields to handle uneven depth distribution. As shown in figure, the completeness of features is maintained throughout the depth feature upsampling process, and the performance is improved. In addition, our DFU can be extended to multi-layer to further enhance the performance of existing methods based on the EDNET. We conduct extensive experiments on both indoor and outdoor datasets to verify the performance of our method. Following exiting depth completion methods, we employ various metrics for quantitative evaluation. The experimental results show that the proposed DFU can effectively improve the performance of existing methods based on the EDNET, such as single-branch EDNET, dual-branch EDNET, and various LRU variants. In addition, the performance of the method is continuously improved as the DFU deepens, while the magnitude of the performance improvement gradually decreases. In the table, we compare the experimental results of SOTA method and improving method using 3-layer DFU on the Kitty benchmark and NIOV2. The experimental results validate that our method is effective for the single-branch EDNET, dual-branch EDNET, and the LRU base, which is the current SOTA method on the Kitty benchmark. Specifically, the improved LRU base by using 3-layer DFU achieves new SOTA results. The qualitative results show that the improved method has more accurate results in fine and small structures, such as the gap area between two adjacent objects. It's all. Thanks.